All right, good afternoon, guys. Today we're going to be covering 7.6, solving special right triangles. Our learning target, what you guys will be covering on the test is I can find missing sides with special 30, 60, 90 triangles and 45, 45, 90 triangles. So these are the two types of triangles that we'll actually be using in solving for today. So these are our special right triangles. Now, the way that they get their name is all based upon the angle measures of the actual triangle itself. So of course, these are both right triangles because 90 degrees. And then the other two angles will either be 30 and 60 or 45 and 45. So let's go ahead and first check out a 30, 60, 90 triangle. So in these two triangles, we're going to let triangle ABC be an equilateral triangle. Find the side length of CD. Now, since this is equilateral, that means that each side length is the same. They're all 2x in length. Now, on top of that, we also have an altitude. CD is our altitude here. Now, the interesting thing about altitudes within equilateral triangles is that it intersects the midpoint. So point D is the midpoint, and also the altitude is an angle bisector, meaning that's cutting this angle in half. So if the full thing was 60, because again, equilateral means all angles are the same as well, it's also equiangular, then this angle is actually 30 now. It's being cut in half, 60 divided by 2. So we now have a 30, 60, 90 triangle. And if each side length was 2x and AD is half of 2x, that means that AD is just x. So this is the triangle that we're going to be using each and every time that we do a 30, 60, 90 triangle problem. But we still need to find the side length CD. We need to find the length of the altitude. And since we already have two side lengths of this triangle, we can find the altitude by using Pythagorean's theorem. A squared plus B squared equals C squared, where C squared is our hypotenuse squared. So that will give us AD squared plus CD squared equals AC squared. Filling in for the values that I already have for our side lengths will give us x squared plus CD squared equals 2x squared. Now, when I square 2x, it will give me 4x squared. So now we just have x squared plus CD squared equals 4x squared. 2 squared is 4, x squared is x squared. Again, we're trying to solve for CD, so I'm going to get all my x squareds on the same side. I can do that by subtracting x squared from both sides. 1x squared minus 4x squared leaves us with 3x squared. So CD squared equals 3x squared. To get rid of the square, we take the square root. What I do to one side, I must do to the other. The square and the square root will cancel each other out on the left side, leaving us with just CD. And on the right side, we'll have radical 3 times x times x. Again, if you see a pair underneath your radical, a pair of numbers or variables, we can take the pair outside of the radical. This will leave us with CD is equal to x times radical 3. And that is the final answer for this side length, CD. Now, looking over at our next triangle, triangle ACB, same type of setup, same exact thing. I'm going to use the triangle that we just solved for in order to solve for CD in this triangle. So first off, we're just going to map up corresponding sides. I see that AC is 2x, and that'll correspond with this AC, which is equal to 9. So therefore, we can say 2x equals 9. From here, we can go ahead and solve for x. Dividing both sides by 2, we get x is equal to 4.5. What that means is that segment AD over here is going to be 4.5, because AD is equal to x, and we just solve for x. So since the side opposite 30 is just x, that means that the side opposite 30 is just 4.5. Lastly, we need to solve for CD. I see that CD is equal to x radical 3. So CD equals x rad 3. Do we know what x is? Well, yes, we just solved for x. X is 4.5. So I'm going to substitute 4.5 in for x, and that leaves us with CD equals 4.5 rad 3, which is about 7.8. All right, so this is how we're going to be using 30, 60, 90 triangles. Let's try out a couple more examples. And again, just to recap, because this can be used, sorry, again, it's equal to 7.8. This can be used for any 30, 60, 90 triangle. So this is what we're going to use for each setup. I'm going to draw this triangle, and then I'm going to map corresponding sides to it and set them equal to each other. From there, we can go ahead and solve for all of our remaining sides. Now, you may be wondering, Mr. Garner, does SOHCAHTOA work for this? Yes, absolutely. You can use SOHCAHTOA at any point. You'll get the same exact answers, and that's the interesting part. So if you want to use SOHCAHTOA, if you want to use your trig functions, you can. And typically, this leads to trig functions because this is just taking a ratio of any 30, 60, 90 triangle, which this is right over here, and it's setting it equal to a similar 30, 60, 90 triangle, and then allowing us to solve for the sides. That's the same exact thing trig functions do, but they don't just do it for 30 and 60 degree angles, they do it for any degree angle within a right triangle, of course. So this kind of leads us into more advanced trig, and this is the basics of being able to set up that ratio. So let's go ahead and try out some examples. Here's our first example. We're going to find BC and AC. So looking at this, the first thing that we always want to do is we want to check our angles first. So I see that we have a 60 degree angle and a 90 degree angle. By the no choice theorem, angle A must be 30 degrees. So therefore, I'm going to draw a 30, 60, 90 triangle right next to it. Of course, the side opposite 30 is x, the side opposite 60 is x rad 3, and the side opposite 90 is 2x. This is the same exact triangle that we just solved for a minute ago. From here, I'm going to map the corresponding parts together. Segment AB, which is 10 units long, is the hypotenuse. 2x is also the hypotenuse. So therefore, I can say 10 equals 2x. And then from solving for x, we get x equals 5. If I look here, the side opposite 30 is x. So therefore, BC will be equal to 5, because that's also x. Lastly, we need to solve for AC. AC is the side opposite 60 degrees, so that maps with x radical 3. So therefore, I can say AC equals x radical 3. Substituting 5 in for x, that would leave us with AC equals 5 radical 3. Now again, we're going to be rounding to the nearest tenth when we're going through these problems. So we're going to enter this into our calculator to get our final answer of AC being 8.7, and again, BC is equal to 5. So those are our two correct answers. So again, set up your corresponding triangle, your similar triangle based upon those ratios, and then just set them equal to each other. Set the corresponding sides equal. All right, next, let's look at a 45, 45, 90 triangle. So let triangle ABC be an arbitrary right isosceles triangle. Arbitrary meaning any, so in this case it's any because its variables are x, so I can plug in any value for x. And then on top of that, we know it's a right isosceles triangle. So if it's isosceles, that means angle A and angle C are going to be congruent to each other by definition of isosceles. If I call them both angle Y, then we should be able to solve for that angle using the angle sum theorem of triangles. So that'd give us angle Y plus 90 equals 180. Combining like terms and subtracting 90 from both sides gives us 2y equals 90, so therefore y equals 45, making this into a 45, 45, 90 triangle. Exactly what we were looking for. Now at this point, we're going to be using this triangle for any 45, 45, 90 triangle that we come across. But first, we need to find the side length of AC. So again, we have two side lengths of a right triangle, so we can use Pythagorean's theorem in order to solve for AC. That'd be AB squared plus BC squared equals AC squared. Plugging in our values for AB and AB and BC, we have x squared plus x squared equals AC squared. Of course, combining like terms, x squared plus x squared is just 2x squared. From here, we're trying to get AC isolated, so I need to take the square root to get rid of this square here. So I take the square root of both sides, giving us AC is equal to radical 2 times x times x. Since we have a pair of x's, we can take them out of our radical, leaving us with AC equals x times radical 2. So that would be our length of our hypotenuse. Again, both legs should be the same because it's an isosceles triangle. Again, this will work with any 45, 45, 90 triangle, so this is what we would draw at the start of any 45, 45, 90 triangle problem. Unless, of course, you want to use trig, because trig will still work perfectly for you. All right, so let's go ahead and check some examples out and try and finish up today's lecture with that. Our first example, find KJ and KH. So we want to find those two segment lengths. Now, again, first things first, we want to take a look at our angles. Determine what type of right triangle this is. Well, I have a 30-degree angle and a 90-degree angle. By the no choice theorem, angle K is 60 degrees. So therefore, I'll draw an arbitrary 30, 60, 90 triangle that we'll use in order to solve for our missing sides. If I look at this triangle, I see that we have HJ. HJ is the only side that we're given. HJ is the side opposite 60 degrees, so that will map onto x radical 3. So therefore, I can say 6 is equal to x radical 3. From here, we want to solve for x, and I can do that by dividing both sides by radical 3. That leaves me with x is equal to 6 over radical 3. Now, you can enter this into your calculator and get your final answer, but since I'm going to be showing you guys the unit circle in a couple lectures, I'm going to go ahead and rationalize this denominator. Again, we don't want a radical in our denominator. So I multiply both the numerator and the denominator by our denominator, by radical 3. So I do radical 3 over radical 3. That's what I'm multiplying by. Of course, this is the same thing as 1, so this would typically cancel out. And that's why it's okay to do this, because I'm multiplying by 1 essentially. This would give me x is equal to 6 times radical 3 over 3. Again, radical 3 times itself, that would give me radical 9. The square root of 9 is 3. And then up top, since 6 is outside the radical, since it does not have a radical, it stays outside the radical. Lastly, I can simplify this down. 3 will go into 6 2 times, giving us x is equal to 2 rad 3, which is about 3.5. We now have kj, because again, kj is just x, and we solved for x as 2 radical 3. Next, we need to solve for kh. We know kh corresponds with 2x, so I can say kh equals 2x. Plugging in 2 radical 3 for x, I'm not going to plug in the 3.5, I'm going to plug in 2 radical 3. That'll give me kh is equal to 2 times 2 rad 3. Of course, 2 times 2 will just give us 4, so kh is equal to 4 rad 3. If we enter that into our calculator, we get about 6.9 units. So again, kh is 6.9, kj is 3.5. Again, very slightly off with the decimal, so I'll be taking a look at that as you guys are working on your assignments. Just try and use the radicals throughout until the final answer, and then round those final answers to whatever they tell you. You may be wondering, could I use trig here? Absolutely, you could have used trig. I could have called this y down here, have 30 degrees, that'd be opposite, and this would be adjacent. So this would be the same as tangent of 30 degrees equals y over 6, or y is equal to 6 tangent of 30. If you enter that into your calculator, you would have gotten about 3.5. I'll actually do that right now. 6 tangent of 30, that is equal to 3.464. Of course, that'd round up to 3.5. So again, you can use right triangle trig with this. It works completely fine. However, I just do want to show you guys these little shortcuts and these little tricks as well. Plus, this will help with our further understanding of the unit circle when we take a look at it. All right, let's try out our next problem. Flub is a square. Find the length of LB. So if flub is a square, I know that all sides are going to be congruent at 9, And all angles will be 90-degree angles by definition of a square. Further, since a square is also a rhombus, our diagonal, LB, is an angle bisector, meaning it's cutting angle L in half, it's cutting angle B in half. But if it's cutting those angles in half and they're 90 degrees, that means that they're going to be 45 degrees each, giving us a 45, 45, 90 triangle. So I start this off by drawing up a corresponding arbitrary 45, 45, 90 triangle. At this point, I'm going to map sides together because I have my legs. Both my legs are x and they're equal to 9. So I can say x equals 9. And that would tell us that LB, our diagonal, maps with x radical 2. So I can say LB equals x rad 2. Well, since we already have x, I'm just going to go ahead and plug in 9 for x. I'm going to substitute it in. And that'll give us LB is equal to 9 radical 2. If you enter that into your calculator, you get about 12.7. So that would be the length of LB, our hypotenuse, our diagonal. Further, the exact answer would be 9 rad 2, but oftentimes you'll need to enter it in as a decimal on your homework. And our final question of the day. Find the length of AC. So I take a look at this. First thing we want to look at is the angles. I have a 90-degree angle, and I see that we have two congruent angles here. So if this is 90 degrees, I only have 90 degrees left between angle B and angle C. And since they're the same angle, that would make this into a 45, 45, 90 triangle. So I can draw out my corresponding triangle here. Now, again, I want to make sure it has the same orientation, meaning it's facing the same exact way, because it's much easier to map the corresponding sides together by doing that. Now, looking at this, BC, side length of 4, maps with x radical 2. So I can say 4 is equal to x rad 2. From here, if I want to solve for x, I divide both sides by radical 2, and that leaves us with x equals 4 over rad 2. At this point, I'm going to go ahead and rationalize this fraction by rationalizing the denominator. So I'm going to multiply both the numerator and denominator by the denominator, radical 2. That'll give me 4 times radical 2 over radical 2 times radical 2. Well, the radicals will cancel in our denominator, leaving us with 4 rad 2 over 2. Lastly, we can divide 2 into 4 twice, leaving us with x is equal to 2 radical 2, which is about on the calculator 2.8. So therefore AC, since both AB and AC are congruent, because again isosceles, therefore they are both 2.8 in length. All right, guys, if you have any questions, have any comments, need any help, anything like that, please feel free to reach out at any time. Thank you guys so much for watching, and have a great rest of your day.